We are so excited to welcome Professor Dan Sitzo back to our show today. So welcome, Dan. Dan is a professor of atmospheric science, and he's also the department head of the Department of Earth, Atmospheric, and Planetary Sciences here at Purdue University. So thank you again for your time and for joining us, Dan.
Well, thank you for having me back. It's a pleasure to be back on the show.
Now, we planned on bringing you back anyway, but this one worked out well because I know that we were in a staff meeting and someone had asked you, being at least they were smart and asked an expert, if they should be I don't know, I think she was ready to seal her house and lock herself up and for 40 days and 40 nights with all the
blankets, yeah,
all the publicity with this with Dustpocalypse or the Godzilla, what they call the Godzilla dust storm? Is that what I saw?
Yeah, the Godzilla dust storm. That's the one that got everybody.
And so we need someone that knows what they're talking about rather than someone from the news kind of explaining this to us, and so we know really what's happening.
Absolutely. Well, I'm glad to be here, and I hope I can clear things up and hopefully tamp down the panic for everybody.
So I guess let's talk street cred real fast. Let's throw your street cred. Just in case someone hadn't listened to your, I mean, I'm sure once they listen to this one, they'll go back and listen to your one from last season. But let's talk street cred. And so, what makes you an authority on stuff happening in the atmosphere?
Yeah, absolutely. My background is as an atmospheric chemist, so professor of atmospheric science, and our specialty in our group is to try to understand the small particles in the atmosphere. So we commonly call these aerosol particles. I'll try to use that term today. But these are the really small particles that the human eye can't actually pick up. So on average, they're something like 1/50th of the diameter of a human hair. So too small to see, really. But they're really important in our atmosphere. They're important for things like human health because we're always breathing these particles in. But they also act as the seeds that water clouds and ice crystals form on. So they're really important in our precipitation. They also act to scatter sunlight coming in. So they give you that hazy sort of view, the one that we've been seeing on the news the last few days with this dust storm. But they also can influence the outgoing radiation from the planet, the heat that the planet's giving off. And so they're really complex players in the energy balance of the Earth. So they're players in global climate change, global warming.
Very nice. Well, it definitely sounds like the dust would be something you could explain a lot better than most people. A little bit more than your average bear on that one. But what's this you were doing with NASA and instrumentation real fast before we jump into our content?
Yeah, absolutely. So one of the instruments that my group is called a single particle mass spectrometer, and that sounds like quite a mouthful. But essentially, what it's able to do is we bring these small particles from the atmosphere into the instrument one at a time. So that's why we call it a single particle instrument. And then we hit it with a laser, a high energy laser. We ablate that particle. We essentially split it apart into its component pieces. And then we can look at those in a mass spectrometer. So we get sort of what you would call the chemical fingerprint of a particle one at a time. And we've actually deployed it, Stephen, as you just pointed out, on a number of different NASA research aircraft. And, this is several years back, but we had a chance to actually deploy it out of a base in Florida. And we flew through one of the dust storms, a much smaller dust storm than this one, but we had a chance to do chemical fingerprinting of the dust particles in these Saharan dust storms and actually look at one, see it up close and also get data from it.
That is so cool.
That is.
And so it's wow, all your research is built up to this podcast. I mean, I think
That's right.
This is fulfilling your life purpose. Don't tell your wife I said that. She might disagree.
It's just between us.
Yeah. And so when you say Saharan, I'm thinking when you say that, it's like, well, it's like Sierra Desert, and that's nowhere around me. It's is it the same?
It is.
Where really coming from?
Yeah, so we should probably take a step back, and this is how we'll tamp down the panic, especially when we give these things names like Dustpocalypse or the Godzilla dust storm. These are actually very common phenomena. They happen all the time, and so they've been going on for at this point, probably thousands of years. And it's a summertime feature. It's part of the trade winds. And so what happens is that you have material that's picked up off of the arid regions of continent, predominantly in the Sahara. We can talk a little bit more about that. This material gets brought up and then it moves from east to west, and it will finally end up somewhere typically over the Caribbean, sometimes over the Amazon, depending on the time of year. And that's important. It's something that we can talk about in terms of fertilization later. And then sometimes what these will do is they'll actually make it over the continental US. You'll see them over Florida, and that's where we sampled them several years ago. And then they sort of break up, and you'll find them over, the lower 48 states, really. And so this last storm was a very large one. It was what we would probably call a 50-year event. It hasn't happened since, the 1960s, probably maybe even earlier. And little bits of it made it as far north, we think, as, Minnesota, southern Canada, places like that, in fact, the last few days.
Wow.
Well, that's amazing that particles can travel that far.
Yeah.
I mean,
Yeah,
wow.
no. And this happens all the time. It's actually quite a common feature where, particles will sort of get a ride on the wind. And so, there's other examples of this. For example, California will often see particles that have come off deserts in Asia that have made it across the Pacific, or they'll see pollution coming out of Southeast Asia. And so very often you'll see California passing their sort of particle standards or their air quality standards, not due to anything happening there, but the material that's coming in. And that sounds like we should be blaming people that are west of us, but you have to think that Europeans blame the US for particles that are coming off of like the eastern seaboard and making it there. So the whole world, sort of sees particles from whoever's upstream of them. And they can circuit the world several times. And this happens very often with things like volcanic plumes. We can see them on satellite just, essentially circling the Earth a few times.
Wow. I think that's so neat that even satellites can pick up that imagery of those particles. So,
Yeah,
Yeah,
so
well,
for your viewers, they should do that if they have a chance to look at any of the NOAA, National Oceanic and Atmospheric Administration satellite products. There's some beautiful images of this. And then NASA runs an imager called MODIS. And so NASA's MODIS instrument has a lot of really nice products that you can visually see these dust storms moving across the Atlantic.
oh, that's great. We'll include links to those. Good.
yeah, we'll put links in the description so people would find those a little faster.
Yeah.
Great.
It just amazes me that a particle, and I've known this of being a little more on the geology side, for me and my background, or interest in study, and I know that we find in geologic record where a volcano has went off, and we anywhere in the world. I mean, it's sometimes those are pinpoints. Oh, okay, we found the volcanic ash here, so we know this layer is that old. And so when we're talking about relative dating, and so, but it amazes me, how big is a particle if it could travel all the way around the world?
Yeah, that's a great question, actually, because the size does dictate how far they're going to make it. And Stephen, volcanoes are great examples of this because people have probably seen these images of volcanoes spitting out a huge boulder, and for a few moments of time, that's an aerosol particle. It's a really big one, but it's airborne, and it's going to come down rather quickly. But as soon as you start getting to the micron size, and so, these micron sized particles are the ones that are like a 50th of a human hair. So, I don't have as much as I used to, but if you can tug and pull a particle, a hair out and look at it, and then think about, 1/50th of that, that's the ones that we're talking about. And they gravitationally settle actually very, very slowly. So it can take particles that small and smaller days to really weeks to fall out of the atmosphere. And that's why they can get these rides around the planet. And so talking about volcanoes again, you sort of see this stratification where the very large material falls out very quickly right next to the volcano. And then as you move downwind, you get smaller and smaller and smaller and smaller particles as you move down. So you can actually track back to where the volcano was by walking up the gradient of particle size for the most part. Then as you get to smaller and smaller particles, they can be quite far downwind, but they've all gotten a ride in the atmosphere for a period of time.
Very neat.
And so the dust that's getting here from the Sierra area, is that small? I mean, or this whole dust storm that's actually affecting the horizon when we see our how well we see. for a distance. It impacts that. I mean, it's one of the programs we're part of is the GLOBE program, and that's one of the things they look at. You know, how is it hazy? How far can you see? How clear is one of the protocols they use for their citizen science program. And so, how large are the particles to impact that we're seeing on the news now?
Yeah, so these are anywhere from about micron size to a few microns, 3 or 4 microns in size. They can be somewhat larger, but those are again the ones that tend to fall out or gravitationally settle more quickly. So you can kind of think about like the median size or the middle size being a few of these microns. So 1/50th to maybe 1/25th of a human hair in size, kind of on that range. And those are the ones that are making it across the Atlantic from the Saharan desert. And so, if your viewers and listeners want to look at some more images, they can look at the visibility in like Puerto Rico over the last several days. You can actually see that sort of haze, and that's all dust from Africa that's made it across. It's typically sort of lofted on a warm, dry sort of wind to a few kilometers, something over a mile in altitude. It comes across the Atlantic in a couple of days, and then it sort of subsides and makes its way, so that it's at the surface, and that's what we're seeing for these hazy conditions on the eastern seaboard in Florida, places like Puerto Rico, or all across the Caribbean, the Dominican Republic, and so on.
And something like that happens. I mean, you said yearly, so every year this pretty much every year this happens.
Yeah, so I was joking as we were getting started today that I was having to look up some numbers and do some calculations, but essentially, if you have the right conditions, if you have this sort of east to west flow, you have relatively dry conditions in Africa that allow this material to be produced, high enough winds to pick this material up. These systems are coming over every few days, sort of every 3 to 5 days. Dust storms do come over annually, and they're usually periodic. So it's, kind of like storms that we get here. You get a storm and a few days of clearing in a storm. And that's what's happening here. So, the Godzilla dust storm, Dustpocalypse, really sort of, hit the continental US 3, 4 days ago. And there's another one that's due in. It's smaller, but it's going to be sort of making landfall in the Caribbean, very shortly here within the next day or so. And that's sort of the periodicity of these storms, that 3 to 5 day period.
And
Oh,
you had mentioned when we first started talking about this, that this is sort of this helps with like the Amazon, like maybe fertility and or fertilizers with the Amazon. So what's involved with that?
Yeah, we said we'd talk about the good and the bad of these dust storms. And so, the haze issue that you guys just mentioned is obviously something that causes problems, visibility and air quality, because as humans, we're breathing in these particles, and especially folks that are prone to respiratory illnesses, breathing in a lot of particulate mass is not a good idea. But Sarah, as you point out, there's good things about these particles too. And one of the things that has been studied pretty extensively is that these particles bring a lot of the material over that plants, say in the Amazon or in the Caribbean, need. The one that's often looked at is phosphorus. These particulates can be rather rich in phosphorus, but other trace elements as well. And so people have said things like, we wouldn't have an Amazon rainforest if it wasn't for these Saharan dust storms fertilizing them every year. And so they're bringing this material in. It's been noted that they probably do things like fertilize Caribbean islands and the coral reefs around those islands by bringing these necessary materials over. Although they do have a possible negative impact on reefs as well, which is that they can transport pathogens. They can, bring material over that has a detrimental effect. And fertilization doesn't sort of have a favorite, so it can fertilize things like algae blooms, which can actually have destructive properties as well. And so there's good and bad here, but I think for your listeners and your viewers, one thing to get across to them is that it really is part of the global system, and it's an important part that does things like fertilize forests, fertilize reefs, and things like that, as well as causing the respiratory illnesses that we've been hearing about recently.
What a great example just of the interconnectedness of globally, like all the spheres. I think that is just, I had no idea this happens annually. And then to hear you say that, that the Amazon rainforest in the Caribbean, that's probably, they thrive because of these annual dust storms. That's just awesome. I don't know. I don't have words.
No, I mean, as a scientist, I think it's fascinating too. It's really the interconnected nature of the planet, and that everything has sort of built up these ecosystems that are so intertwined and so dependent on one another.
It makes the world seem like a much smaller place when we start looking at it this way, isn't it?
Really
It's
true.
it is a system. We talk about ecosystems and how everything's a system, but until you see something like this and realize its purpose within our system, what role it plays, I should say, in our system, you don't really think about how interconnected the entire world really is.
Yeah. Let's see.
So, like I said, I was going to say something, but I saw Sarah getting ready to pop up.
You go ahead. I need to think about it.
Fair enough. All right. So within your research and knowing that we have all these particles coming over, what kind of impact does that? What are more impacts that it could have? I mean, I'm sure it's more than just fertilizing different smaller ecosystems, but I guess what all are you looking for when you're looking at this? I mean, I'm assuming it was a lucky thing that you got to fly, you got your machine to fly through a storm, so you could do have more data. But what are you looking for out there?
Yeah, no, thanks for asking, Stephen, because I think that depending on what kind of a scientist you are, if you're in a medical field, you're going to be really interested in the impact on human health, and if you're into land systems, you're going to be interested in this fertilization effect. One of the specialties of our group is looking at cloud formation, and so Stephen, you mentioned some of your geology background, and one of the things that we've been doing recently is looking at the mineralogy of these dust particles. And now, not all mineral dust is created equal. And so this is obvious to a geologist. They can look at a rock and look at the different minerals. We've easy as atmospheric scientists in the past, and we've just sort of thought, mineral dust is mineral dust. It's all the same. And in the last few years, we've started as a field to understand that certain minerals are better at forming clouds than others. So things like feldspars, for example, have a crystalline structure that's very good at nucleating ice. And so if you have a couple of mineral dust particles, some will preferentially form ice clouds, and then start precipitation over others. And so this was one of the reasons that we were really interested to fly through the Saharan dust storm when we had a chance to off of Florida these several years ago, was that we got to look at this chemical fingerprint of the material. And then you can imagine you can have, we didn't get to do this, but you can have, fellow researchers, colleagues that are on location, that are in the Sahara, that can pick up this material and bring it back to you. And then you can do studies in the laboratory to pinpoint exactly the conditions, the temperature, the relative humidity that it'll form a cloud. And then that information will then find its way into things like global climate models, so that we can better understand when clouds are going to form in the atmosphere, where they're going to form, and so on. And so very selfishly, that's our research, and that's why we're so interested in these particles, is that they're these very fascinating, unique mineral particles, but also very good at forming clouds, which have this impact on precipitation and radiation.
Oh, and when you say radiation, are you also looking at like the Earth's energy budget, to see what's our albedo effect, what's more reflected, and what's saved?
Yeah, I should be careful, by the way. I'm not meaning radiation like coming out of a nuclear reactor.
Yeah.
It's this term that we often use, the Earth's radiative budget. And really, it's this balance. It's this incoming sunlight versus the heat of the planet being put up. Where that's being absorbed, where it's being, reflected from, and so on. And so that's exactly what we're looking at, is, where are these clouds forming? Where are they able to reflect sunlight? Where are they able to trap heat? And it can get very complicated because, you can have things like low clouds and then a dust layer and then more clouds above it. And so adding all of that up in a global sense is what these models do very well.
And so when you work with models, there's a couple directions I want to go. I'm trying to narrow myself and focus myself in. But when you work with the models, what all is your role? I know some things that we've talked about before. It's like Sarah and I was teaching some things using Arduinos. And more classrooms are integrating computer science into the sciences so that students understand real world applications. And you mentioned, oh yeah, we have Arduinos on the instrumentation that we fly with NASA. I'm like, oh, okay, that's super cool. And so what all is your role and with the model? Are you just collecting data for a model? Are you talking to like someone programming things? Do you help program? How does this team work together?
Yeah, it's another great question. Thanks for asking. So I know just enough modeling to be dangerous is I think the way that I like to put it. Um, I, I actually had a chance early in my career to spend a few years at the Swiss Federal Institute of Technology in Zurich. And I worked for Ulrike Lohmann, and she is one of the leading experts in global climate modeling, especially with respect to clouds. And I was really excited to have the job with her group because it allowed me to, sort of see how models are built, how they're developed, sort of how the sausage is made. Um, our group really is making the feedstock for those models. So those models are really, as the modelers say, only as good as the data that they're inputting. So you can imagine this topic that they could say mineral dust forms clouds at some set of conditions. Our group is responsible for trying to pinpoint what those conditions are so that the parameters used in the model are correct. So we might say that this particular type of particle forms a cloud at this temperature and this relative humidity, and then that's what they use in the model. So that's what we're producing for them. But it is really important, I think, for scientists in our field to understand both sides. If you're an experimentalist like myself, it's really important to understand how the models work. And for the modelers, it's really important to understand the limitations, the uncertainty on the experiments, because otherwise we're never going to get this right. So that's why I've been very lucky in my career to work with folks like that. And I think it's something that we all should strive to do more.
I mean, I like that. It's our oven went out at home, and so it's like we're looking at ovens, and I'm looking at the features. I'm like, well, you could tell the engineers designed the oven talk to the bakers, And so to me, it's kind of like what you're doing. Is if the people designing the models not talking about to the people researching the input, it's not going to be as good. And so that communication and that connectedness of teams, it's just it makes sense. Although sometimes we forget to do it. And so I really love when I hear scientists like yourself sharing how they get some information so they can basically know the lingo and be able to communicate back and forth.
And Dan, I just wanted to point out too, I really appreciate too that you brought up the uncertainty of those measurements as well, because I know that in high school chemistry, that's a really difficult concept to get across to students. So then to hear like scientists like you that has to look at the uncertainty of different measurements being taken, I think that's just something really important that this really is a thing that you do have to pay attention, that there's always going to be a little bit of, I don't know, that you just have to be careful that when you're making measurements, like how many places that with certainty. And so thank you for bringing that up.
Oh, you're very welcome. It is really important, and for the listeners and the viewers out there, just this understanding of, how well you do something and then propagating that through the whole system. Because, like using this example, if a modeler were to think that we made a perfect measurement, which nobody's ever made a perfect measurement before, you could fool yourself into thinking that your result is then perfect. And if you don't propagate that uncertainty through the whole system, you'll never have a real understanding of what the possibilities are. So no, it's a great point, Sarah. Thank you.
Yeah, with uncertainty, that's something that I guess I had not thought about. I mean, through high school, even my undergrad, until I started working on a geology master's in Daryl Granger's class, where we had to calculate the percent of uncertainty. I never would have thought you could calculate this percent of uncertainty of a thing, and to know that that is something that you have to do whenever you're collecting data is, I think it's a really, really cool thing.
No, it definitely is. And really doing it at all stages and making sure that you understand each of those steps and how it affects the next step is really important. And I think we're all saying the same thing, but doing the handoff properly, like the person that's taking the data and the person that's using the data have to really agree on that and make sure that they both understand it, that you're sort of handing off the right uncertainty and that you're accepting the proper uncertainty is really important in our field, especially when we have these different groups working together.
Absolutely. And I like how you stated that as well. You know, you could have different groups all over the world that are working on different pieces of those. And so absolutely you have to understand, like you say, where you're leaving it and where the next person's picking it up. So definitely.
Mhm. And yours is used in more than just like an energy budget model. It's like when you're collecting data about the storms, there's a lot of different models who need that data to be able to do things. So one that we'd mentioned, I know it was like Dan Chavez isn't here with us, but he does hurricanes. And so he needs that data that you're collecting as well as an input, doesn't it? I mean, you had mentioned that in our staff meeting.
Yeah, no, that's a great point, Stephen. Thanks for bringing it up. Yeah, sort of going back to the whole dust storm idea, these are really fascinating events, and one of the other things that they can do is impact hurricanes. And so, again, I defer to Dan Chavas on this. He is our expert in EAPS at Purdue, and a fantastic scientist on this topic. Um, what he's probably talked about and what's well known is that there are a lot of hurricanes that form in this sort of birthing ground that's off of the West African coast in sort of the East Atlantic. And what we're talking about are these dust storms that are coming off of the African continent, and they're obviously going right through that sort of birthing area. And so there's been a lot of research over recent years of how these dust storms can interact with these sort of nascent hurricanes that are spinning up and then potentially, hitting the eastern seaboard, the Caribbean, that area. And so, in a general sense, what's believed is that these dust storms are very dry. So they represent a layer of air, as we just talked about before, a few kilometers, something over a mile in altitude, and they go right over these birthing areas, and they can effectively sort of shut down the formation of hurricanes. So that's one area that we think we understand. And again, Dan has probably talked about it, but more dust storms, more dry air, probably less birthing of hurricanes. It does get a little bit more complicated because there's some dynamics of the movement of air. Does that sort of graze the hurricane, or does it go right over the top of it? Does it shut it down, or does it somehow impact it? Could it actually intensify hurricanes? And that's, I think, where the field is at right now, is trying to really understand these dust storms, the particulate matter in them, the dryness of that air, and how it's going to impact that sort of birthing area for the hurricanes.
Now, when you said particulate, it reminded me because I know that is like once again the GLOBE program. They have a little particulate activity we do with elementary students, collecting large particulates they could see. But when we get the EPA report about air quality, what is it the same size, the 1 to 4 micron type thing where the dust is? Is that what it's talking about, or is it generally talking about larger, like the pollen size, the larger pieces?
Oh, great question. You guys are loaded with great questions. I love it. Yeah, so let's help the viewers and listeners out a little bit on this. So when you see EPA standards for particulate matter, it'll usually come with this little statement of what they're talking about, and we have to sort of decode it. Very often they say PM1, PM2.5, or PM10. And so PM is particulate matter. It's the amount of particles. And then the number is the size and lower. So when it says PM1, it means 1 micron and lower total particulate loading. And that's usually a mass. PM10 is going to be, Stephen, that larger size, 10 microns and lower. So now we're talking about all probably of the dust, or almost all of the dust. And now we're starting to talk about some of these bigger things like pollen grains or spores, things like that. And so now you're starting to get into the stuff that causes people to have allergies and, sneezing and stuff like that. So, and then of course, 2.5 is 2.5 microns. It's sort of something in the middle. So it's important that number and realize it's always going to get larger because you're adding more and more larger particles into that loading. And then the EPA will set different standards for, how much is unhealthy, how much creates an action day, when do people that have respiratory illnesses need to pay attention. I hope that answers the question, but that's the general idea here. This dust that we're talking about is, this sort of sitting at a few microns in size. So most of it's going to be in PM 2.5, and then, the bigger particles will fit into this PM 10 range.
Oh, very good. Very
Okay.
good. Yeah, I know that's something that some of the programs that we work with is working on, doing like national protocols to do a big network of that. Anyways, was it Tracy that mentioned that?
Yeah, Tracy did, and yeah.
Yeah. And so we're excited to see that come up because that's something when we do the atmospheric chemistry, we now do particulate matter. Is because you mentioned the counters that we could get, so we got some of those, and we always do those with students in different areas, and to be able to talk about air quality, and that definitely helps you understand.
Yeah, speaking of Arduinos, this is one thing that the field has done a really good job of is that, even a decade ago, these particulate counters were really research grade, very expensive instruments. And folks listening to this pod will be able to say that, they could go online, do a search, and for, $100 or maybe just a little bit less, pick up these little personal air quality monitors that'll give them these PM1, PM10 numbers now. And I've even seen these ones you can wear them like on a lanyard around your neck. And this used to be something that was only found in like a clean room, and now you can walk around your house with one if you want to.
And how accurate for something, if someone is just going to go on and buy something like that, like how accurate is that? Like $100 ones.
Yeah, it's great. So it goes back to our uncertainty thing. So these personal ones, the inexpensive ones are certainly not research grade. So in the lab we might want these to be good to 1 part in 1,000 or something like that, or even higher. And if you measure it within tens of percent, it still gives you a pretty good idea for personal exposure, or for these small teaching grades. If we talk about 1 microgram per cubic meter of air versus 1.1, it might not make that much difference. It's the importance is the difference between 1 and 10, whereas in the lab we might want to know it to 3 or 4 decimal places. So yeah, these personal ones might be good to some tens of percent, but that's often good enough to say, it's a really clean day or a really dirty day.
Okay.
Oh, very nice.
Yeah.
Very nice. I like that. All right, Sarah, any last questions?
I can't think of anything right. I mean, I know, yeah, probably, but this is fascinating. Thank you so much for explaining this dust. I had heard about it in the news, and it helps to hear it from someone that does research on this.
Well, thank you both for the invitation to come back. It was funny, as Stephen mentioned, we were just talking about it off the cuff the other day. And then he said, "Oh, would you be interested in coming back and explaining it?" And yeah, it's fun. It's a personal interest. It's an interest of our group, and so it's great to be able to talk with you about it.
So we certainly appreciate it. You just hear things on the news, and it's like, it's nice to know, do you panic or do you not? Is this an anomaly, the world-ending event? Is that what happened in here? I mean, they kind of make everything out to be that these days, especially. They fear-monger a little bit. So it's nice talking to someone who has spent a lifetime researching this and actually getting answers from an expert.
Great. I'm glad to help out. And, hearing Dustpocalypse versus just a 50-year dust storm is going to have a different connotation to folks. So I'm glad we could tamp down some of the panic.
Yeah. I don't think I'm ready to sell my real estate because the Dust Bowl is coming now. Yeah. Well, thank you again for your time. We appreciate it. We'll let you get back to your research.
Thanks for having me. Take care.
Thank you for listening to our podcast. Please hit the subscribe button so you'll continue to hear about new and exciting STEM-related work being done.
Tweet us questions, suggestions, and requests at Purdue SOS, or email us at k12science@purdue.edu.
Until next time, be super, and remember, you are someone's hero. Boiler up!
Hammer down.